Hi, my name is Hwason, and I'm a recent graduate from Korea University, where I majored in statistics and computer science. I began studying machine learning and deep learning around 2 years ago, getting, uh, yes, I think uh, fourth page, maybe. Yes. And I'm getting my started through Kaggle competitions. Since then, I have participated in numerous competitions on Kaggle, and I'm very lucky to have achieved first place in this competition. This competition was particularly meaningful for me as I have an interest in developing real-time applications utilizing AI. And next slide. Yes. The goal of this competition was to create a TensorFlow Lite model that can classify signs from the American Sign Language. The data was initially extracted from MediaPipe Holistic model, which provided us with a XYZ coordinates of landmarks from hands, ribs, nose, eyes, and certain body parts. Next slide, yes. The workload I took in this competition was very straightforward. I continuously improved these four components of the model. I first identified a model that was effective, then worked on enhancing the data processing method. And as my model's accuracy improved, I implemented more regularization techniques to enhance the model's robustness. And lastly, I tried to compress the model. The model compression is usually used to reduce the number of parameters while maintaining its accuracy. By continuously iterating this workflow, I was able to incrementally improve the model's performance and efficiency. In my point of view, this strategy was most effective in enhancing the key elements in this competition. And next slide. Selecting the appropriate type of model was the most crucial point in this competition. My solution ultimately was an end-to-end neural network classification model. The model combines a one-dimensional convolutional architecture with a transformer architecture. I used the TensorFlow for development and Google Colab's TPU environment. Changing the data to the TF record format helped me to accelerate the training speed. Training took approximately 3 to 4 hours per model on Collapse TPU V28, with a single model having inference time of 15 milliseconds per video. And next slide. There were many data preprocessing methods I could try in this competition. However, it was very difficult for me to find effective methods among the various ones I tried. In the end, I adopted a very simple approach. I only used XY coordinates of and hand landmarks. And then I added lips landmarks, which led to noticeable performance improvement. Finally, I also included eye and nose landmarks. The body positions did not help me improving the performance. Next slide. There were many data preprocessing methods I could, no, this one, okay, where I attempted many feature engineering methods. The one that helped me was the motion feature. The motion feature of leg 1 showed quite a significant performance improvement, and leg 2 showed a slight performance improvement. From leg 3 and so on, there was no improvement. The data extracted from the MediaPipe holistic model was already normalized between 0 to 1, but additional normalization on individual data was helpful. In my case, I used 17th landmark located on the nose as a reference point. That is, I standardize each sequence by making the coordinates of 17th landmark the mean for each data. This was significant for stabilize the training. I chose the 17th landmark because it tends to be located near the center point. And next slide. One of the major characteristics of the data set is the significant variation in the number of frames between videos. We could ensure that our videos have the same length by using padding or interpolation, but this is not an optimal solution because it leads to information loss for long videos and introduces unnecessary information for short ones. So I implemented the model to handle variable input lengths. Once the model can handle variable input lengths, it can make predictions without padding during inference, thus maintaining the original input lengths. This approach significantly reduces inference time. To maintain train test consistency while handling variable length input, accurate masking implementation was necessary. One of the core components of my solution, which I discuss later, is accurately implementing masking in 1D convolution layer. In my implementation during training, we passed to a fixed length such as 384, and during inference, I processed the input as it is. The pre-processed input ultimately takes the form of a 2D tensor, which can be directly fed as an input to 1D convolution layer or a transformer block. And next slide. Let me describe the model. The primary feature of my model is the use of 1D convolution. A pure 1D convolutional neural network was sufficient to achieve very high accuracy, reaching a score of 0.80 on the public leaderboard. I later found that including a transformer block on top of 1D convolutional block could even achieve higher accuracy. And next slide. Here is the entire structure of the model. It's just simple end-to-end neural nets, and all the model's operations have been implemented to consider masking. For instance, even for global average playing at the end, it ignores the value of the padded timeframes when calculating the average. The output is connected to categorical cross-entropy rules, taking on the form of typical classification model. Next slide. The blocks that make up the model have the following structure. Initially, a single model uses a dimension of 192, and 3 1D convolutional blocks and 1 transformer block are connected. This entire structure is repeated twice. Each 1D convolutional block has a structure similar to the inverted bottleneck architecture using depth-size convolution as proposed in MobileNet. The differences are fewer batch normalization and activation used, and instead of SE module, I used ECA module, which uses much fewer parameters and computations. And next slide. And for accurate masking support, our model operations must be able to ignore the padded time frames. Here we assume that padding only occurs at the end of the input. The easiest way to implement masking in time series data is to maintain the time frame information of the input sequence. Simply, if you prevent operations at its time frame, referencing data from future time frames, the index of the time frame that should be masked remains the same, making implementation straightforward. For example, in the situation where padding equal to same is primarily used, the corner passes its time step. The data corresponding to the future of each time step is also included in the corner calculation, meaning the third frame in this example, after passing the convolution operation, uses the path token for the calculation. But as we do not pass during inference, the calculation results of the third frame differ between training and inference. The train test inconsistency occurs in the third frame's output when using padding equal to same argument. In this case, implementing masking becomes much more complicated. On the other hand, when using the padding equal to cursor argument, padding is only applied to the front of the sequence, preventing each time step for seeing data from future time steps. This way, the original time step information is maintained. The outputs of first, second, and third time steps that do not correspond to the padding part of the input maintain the same output during training and inference. In this way, the index to be masked can be maintained up to the final output of the model, and overall masking can be implemented just by adding one masking layer at the beginning of the model in TensorFlow. The transformer block originally designed to support masking with tension mask, and TensorFlow supports masking in layers such as batch normalization and global average pooling. So masking could be implemented relatively easily, and through this, I was able to achieve both high accuracy and fast inference time. And next slide, please. Next is it is training, and it follows the end-to-end supervised learning with a neural network classifier. The model was trained from scratch, and when submission, our data was used without validation. For identical model using different seeds were used for submission. Next slide. As the model is trained from scratch, regularization played a crucial role. First, stochastic depths, known as drop paths and dropout, were applied. Additionally, adversarial weight perturbation was applied. Its regularization techniques played a crucial role in preventing overfitting. And if any one of them is omitted, noticeable performance degradation occurs. And next slide. I tried various augmentation techniques, but most of them only brought meaningful performance improvement if they were already well-known techniques in other fields, such as computer vision. Specifically, random sampling, horizontal flip, and random affine transformation significantly improved the accuracy. Next slide. Let's go over the training configurations. Since I trained the model from scratch and applied various regularization, I set the number of epochs very high. I used a cosine decay running late schedule without warm-up and rectified Adam optimizer, which provided better accuracy than a well-known Adam W. An interesting point is that unlike most other teams that used a very large value of label smoothing, there was almost no difference in my case whether label smoothing was applied or not. In the final model, the model that used plain categorical cross entropy without label smoothing showed slightly higher accuracy. And next slide. Here is the training plot of the final single model. Due to the strong regularization applied, validation accuracy continued to increase up to 400 epochs, and it showed a validation accuracy of 0.80 in a 5-fold split by participant ID. When I trained the model on the whole data and submitted, it also showed accuracy of 0.80 on the public leaderboard. Next slide. This is a score improvement of a single model on the public and private leaderboard. Accuracy improved noticeably when the RIFS landmark was added. And eventually, a single model achieved an accuracy of 0.80 on the public leaderboard through the adding various additional features and combination with the transformer. Next slide. One of key elements of the competition was to develop a model that has significantly high accuracy while also being lightweight. Personally, I believe I achieved this successfully. When using a single model instead of 4 models, the size of model becomes 1/4, but the performance drop was not significant. A single model has a size of 3.76 megabytes, a latency of about 15 milliseconds per video, and achieves a second place on the private leaderboard. If the only left and right hand landmarks are used, the accuracy drops about 0.03. When filtering the input sequence to only include frames containing the landmark from the left or right hand, I could see a speed improvement of approximately 2 times, and the accuracy dropped up by about 0.02. I believe there are several other ways to shorten inference time without sacrificing accuracy very much. Next slide. There were several methods I tried but did not include it in my solution. Graph neural network models, which reported high performance on various skeleton data sets, such as kinetics data set, were not very efficient. Because of the characteristic of the data, I was able to try many new augmentation techniques, but so I implemented complex ones that did not exist before, but only the existing simple techniques that widely used were effective. Many other teams successfully used angular and distance features, but I failed to utilize it. I expect this area could be a focus for further improving my model performance. I also tried several other ideas, but most of them probably did not work because they were not implemented correctly. Finally, I want to express my gratitude to Kaggle, Google, and other competition organizers for hosting this meaningful competition. Thank you for listening.
Google Accelerated Sign Language Recognition. This agenda is following. So I'm Yasuhiro Ohkawa. So I'm PhD. I have a PhD degree, computer vision from University of Tsukuba. And I'm currently working as engineer at Toshiba subsidiary. And I'm developing OCR system for postal and logistic automation system. So I'm good at making fast and lightweight recognition system. The summary. So this figure is my overview of my solution. So I will discuss this detail. So, okay. So the key idea of my solution is the dataset contains unnecessary or adversarial effect to recognition. So it is important to remove these and apply learning that is more robust against the noise. I think this is very important. So next is the feature engineering. So I use only 122 features out of over 10,000 features. So using X and Y coordinate and ignore Z coordinate. So, and features points of gesturing hand is used because no information on no gesturing hand. And feature point of the lips is used. So in total, I use 122 dimensional features. To determine gesturing hand, so I use frame of number of detected hand. So if there are more frame for the left hand, the X coordinate is flipped. So this figure on top original sequence. So and bottom figure are flipped to right hand gesture. So this process is very important. Improves the CB from 0.13 to 0.20. It is easy to recognize the gesture. So modeling. So I use one-dimensional CNN because local feature extraction is very sufficient, I think. So for building diversity model, I create two types of 1D CNN. The first is 1D CNN and fixed length. So it classifies fixed length sequence. So all sequences are pre-normalized to fixed length. This model is easy to implement, so no packing sequence and no packing mask pooling. It is very simple implementation. The second is 1D CNN variable length. It classifies variable length of sequence. So this model is faster than 1D CNN fixed length. So both models have a hand backbone and lip backbone and head for classification. So originally, there was one backbone for lips and hand, but separating them improves CB from 0.2 to 0.26. Next is confident learning. So the dataset contains completely unrecognizable data. So in fact, when the data used for training is predicted, the top one accuracy rate is only about 96, not 100. So removing these can improve the performance. So to remove these data, I use CleanLab. Applying CleanLab, about 5,000 sequences were removed. As a result, 0.01 point improvement in public leaderboard and 0.04 point improvement in the private leaderboard. So perhaps private datasets have more easy data and then may be more effective than public dataset. Training method. So training method is very similar with other solutions. So I use three-fold participant cross-validation and in total 300 epochs. And I use stochastic weight averaging is applied after 15 epochs. And I use Adam optimizer and arc margin product and stochastic depth and label smoothing. So important findings. So I did some experiments after competition. Here are some interesting things I found. So first interesting is by applying CleanLab, it can achieve the private leaderboard 0.87. So it is border of gold medal. So without ensemble. The second is ensembling with fixed length and variable length. Outperform ensemble of only fixed length. So it turns out that different types of ensemble is very important. Thank you for listening.